All right, so welcome back. So let's continue talking um, about multivariable systems control or multivariable control. So just to continue, so let me introduce myself quickly. And my name is Professor Lajimi. I got my PhD from Department of Systems Design Engineering from University of Waterloo, Canada, and my master's in Mechanical Engineering from École Polytechnique Fédérale de Lausanne in Switzerland. All right, so let's talk about. We have already talked about a transfer function, transfer matrix, and transfer function. So our transfer function represents the dynamic behavior of the system. We know that, and then we know that up to now you have seen transfer functions mainly as algebraic objects. So there's a difference between algebraic objects. There's a difference between algebraic objects and matrices. Not there's a difference, but we're going to talk about. We talked about why this case of multivariable, multi-input, multi-output systems is different from single input, single output systems. So GS essentially contains all linear dynamics of the system if we fix S as our variable, then the linear dynamics no longer evolve in time, right? Because it is we have fixed the system, so it doesn't evolve in time. So once S is fixed, time essentially disappears, and that's what you would expect, right? Because uh, S varies, but then S varies corresponding to time varying. So if time is S is fixed, essentially we're looking at the system at a certain time. At a fixed of a value of S, the dynamics no longer evolve in time, and the system behaves as a static mapping between complex amplitudes. So static mapping between complex amplitudes. Let's think about a mechanical analogy. You're no longer watching motion over time. So you have dynamics, you have a dynamic system or a system that moves, and then you're no longer looking at watching this system over time. You're no longer watching motion over time, and you're no longer looking at the system over time. You're comparing a steady state amplitude and phases. So we are looking at this map, how the system, the steady state amplitudes and phases would vary. Um, the most important choice is S equal J omega. So if since Gj omega describes the steady state response to a sinusoidal input of frequency omega. So one slide earlier we talked about mapping the steady state responses. Now you're comparing steady state amplitudes and phases, and then to compare steady state amplitude and phases, you're essentially setting S equal J omega. Since Gj omega describes the steady state response to a sinusoidal input of frequency omega, this is what we are looking at. This is not an arbitrary choice. This is how experiments are done. Meaning that when we design the system, we want to test the system, we want to test the control system, we're going to input a sinusoidal signal into the system. We are going to inject a sinusoidal input into the system. This is not an arbitrary choice, and this is how experiments are done. And it matches the reality of systems in the majority of cases. So engineers excite systems sinusoidally because responses are easy to measure. Okay, if you apply an impulse or an impact to the system, the system would respond differently. All right, sinusoids essentially corresponds to harmonic forces. Mechanical systems respond at the same frequency in a steady state. Yes, we are gonna, as we go into the details of system responses, we're gonna talk about the difference in frequencies, but remember, we're talking about linear systems. Linear systems do not create frequency. And we're going to talk about this later further. This is precisely how vibration and frequency sweep tests are performed. So in frequency sweep test, we apply sinusoidal input, but then we vary frequency. So we perform a frequency sweep. Let's think about shaker table tests. So we have shakers in the lab to perform vibration tests, and then swept sign vibration testing, and then frequency response identification in responses. Now consider this consider the MIMO system. So by S is GS DS, where D denotes the input. So you're going to use D here just so in terms of notation we're not going to have any problem later, otherwise you can call it anything. And I do know that conventionally we call input U, but then it doesn't matter, it's just a notation. We're going to use D for inputs. We are, just to avoid any clashes, any notation clashes later, we use D instead of U, therefore, as an input to the system. And then once later we're going to talk about SVD, we're going to go back and use U. At a fixed frequency, the system reduces to Yj omega equals Gj omega, J omega. So I have essentially only substituted J omega for S. That's all I've done. The input is a sinusoidal input, and Gj omega is a complex matrix. It is a complex matrix because we are talking about MIMO systems. So at each frequency the system becomes a matrix. At each frequency the system becomes a matrix. The plant at each frequency is represented by this matrix. So we're going to talk about this further later. And then each actuator, just to remind you, applies a harmonic excitation. In this case, we're going to, because we're studying the system responses for this harmonic excitation. And each sensor measures the harmonic response. So it's a linear system, so we can say for sure that the system responds with a measures harmonic response. Yes, I'm aware of the effect of damping on linear systems, but for now, let's agree this is what we have. All right, so each element of that capital G matrix at J omega represents the response from input J, input channel J, to output channel I. So we talked about this notation, this system of notation, that the index I represents output channel, but the index J represents the input channel. This is the direct multivariable extension of this ISO frequency response. Mechanical examples, we have for example, motors in robotics, excited flexible frame or a flexible arm, or and multiple accelerometers measure vibration, for example. That's the input-output example. So we talked about the order of terms. This is the direct multivariable extension of this ISO frequency, as I said, response. And now imagine that you apply a sinusoidal input at channel J. So we have the channel J, applying sinusoidal input at channel J. The Jt, therefore, is dj0, the amplitude, and the sine omega t plus phi j. And omega is the frequency at which we are essentially fixing the system's frequency at omega, and then we have phi j as the phase of this input, channel J. So think about exciting one actuator, or exciting the system using one actuator. This essentially isolates one column of that matrix, right? The matrix G, capital G at J omega. But essentially what happens is, if we apply only one input, then we are isolating one column of this matrix. This corresponds to exciting the system with a single harmonic force at one actuator. And then after transient's decay, this set response at channel I is yit by I0 sine omega t plus phi. Again, we're talking about linear system. Linear time invariant systems preserve frequency. They only scale amplitude, scale higher or lower, and then shift phase. The linear systems do not generate new frequencies, as I said before. And then, but nonlinear system, which we're going to talk about later, essentially are different. So we need to be aware that the system response, we need to make sure the system responds in linear fashion, or it's a linear time invariant systems. So the gain and phase shift are determined by small g ij j omega. So yi0, just to remind you again, the first index I represents the output channel, and the second index j represents the input channel. So we have yi0, the output, over vj0, because the input at channel j is dj0. The ratio of amplitude is the magnitude of g ij j omega. We're going to see this in an example again, because we said that this small g ij is essentially the transfer function between input channel j and output channel I. So we are specifically targeting these two, and then we're talking about the ratio of these two, and we're going to talk about the phase difference between phi ij and phi I and phi j. The magnitude essentially represents amplification, and the phase talks about timing relationship. The timing relationship between certain channel input, channel j here, and certain output channel, channel I here. So magnitude indicates amplification, phase indicates delay or advance of the response. Let's go to the next slide. Using phasor notation, which you have already seen before, but we're going to talk about this. And you do remember this from your engineering mathematics course, and also control course, vibration course. as many other courses, essentially. Using phasor notation, sinusoids are represented as complex numbers. So dj omega, the input at channel j or input channel j, dj is 0 e to the j phi j, and then yi omega is yi 0 e to the e to the I phi I. Okay, so this is I, kind of not clear, but what the first one is j phi j, and the second one is I phi I. So phasors are not to remind you, phasors are not approximations, they are exact representations of steady state sinusoids. This term, steady state, matters a lot, because if this wasn't a steady state sinusoids, it would have been different. But for this system, the way we are treating this system, this is an exact representation of a steady state sinusoids. So complex exponentials simplify algebra while preserving magnitude and phase. The input-output relation becomes yi omega is gij at j omega, dj omega. So the specific small g of that bigger G, capital G, is the one relating the output I to input J. At one frequency, this is just essentially at one frequency, this is just multiplication. Time domain complexity collapses into linear algebra, right? So we had this time domain complexity, but then now we have linear algebra. We don't anymore have time domain complexity. If multiple inputs are excited at the same time and they're all affecting output channel I, we are only interested in output channel I, and multiple inputs are excited at the same frequency, then we have a sigma over J, and J was the input. So let's, for example, we can expand this G sigma over Gj omega, Gi J, sorry, Gi J omega and Dj omega. The first one becomes Gi1 D I omega, D1 omega, I apologize. And then we have the second term, which is added to the first term, G I2 J omega, D2 omega. So this is essentially superposition, which does apply to linear systems. So contributions from different actuators add vectorially, not just in magnitude, but also in phase. Remember that from previous slide, here we had this phasor notation, and now if you substitute this phasor notation here, you have both magnitude and phase. So you have both magnitude and phase. You should always remember that this follows directly from the superposition principle for linear systems. In matrix form, y omega is G J omega D omega, and the D, the input vector, and then y omega, the output vector, y1 through yl, yl, and then input vector from d1 to dm. All right. This is our matrix, and it is in matrix form. At each frequency, we have a static linear mapping. This prepares us for singular value decomposition later. So at each frequency, omega, we have this linear mapping between input and output. Is frequency defines the static mapping from input vibration amplitudes to output vibration amplitudes, essentially. Sorry. And then at each frequency, omega MIMO big system behaves like a complex matrix. This allows analysis of direction and amplification, energy gain, and then worst case scenarios using matrix tools such as singular values. This viewpoint underlines BIBO and MIMO stability too. And soon we will ask which direction is amplified the most and which direction is the nicest direction, essentially. Although the question which we are essentially focusing on is the worst case scenario and worst case direction, worst case response, essentially. All right, so and then this viewpoint essentially underlies, as I said, BIBO stability, robustness analysis, and observer and Kalman filter design. Frequency domain thinking feeds essentially directly into modern control design. So because now we have kind of related the frequency domain thinking to multivariable MIMO systems. Let's assume that now, as an exercise, consider a 2x2 MIMO system. Both inputs are excited by sinusoids of the same frequency. Time domain inputs, mechanical multiple actuators. For example, as an example, think about multiple actuators often excite a structure at the same frequency with different phase offsets. Now we're going to talk about this application further later. This exercise essentially meant to make the coupling idea concrete. So we want to make sure that we know what coupling means, because you're going to see the cross-coupling or cross terms immediately when both inputs are activated. So if we don't activate both inputs, we're not going to see this coupling. And same frequency, you might think, why same frequency? But the same frequency is not really the a limitation. Think about, for example, a plate, and at various points on this plate, we're going to apply same frequencies, but we're going to apply them with different phases, for example. So this is a concrete real-world example, essentially. Time domain inputs using phasor rotation notation, and then we have d omega at certain omega, because as we said, we're going to talk about, we are transforming this time domain complex system into frequency domain, a linear static mapping between different steady state responses, just to remind you again. So we have 2 degrees of freedom, D10 and D20, and the phase psi 1 and psi 2. Again, for example, 2 shakers on a wing panel in phase excitation can amplify bending, and out of phase excitation can amplify torsion. If you think about that plate example again, if you have both in phase, then you amplify bending deformation, and then if they are out of phase, you amplify torsion deformation. Then we have the phasor notation, as we talked, and at this point, once we use the phasor notation, we stop chasing sinusoids in time and instead manipulate complex numbers. You may think that G, again, just to remind you, e to the j, phi 1 and phi 2 and psi 1 and psi 2 are approximations, but they are not, because we're looking at the system at certain omega, so it's an exact representation for a steady state LTI sinusoidal response. So let's talk about this steady state. Let's talk about the solution of this exercise. The steady state. So my suggestion is you pause the video after each exercise. You do not continue watching. You solve the example and then you start watching the video. So we have the steady state output is obtained by omega, gj omega, d omega, and this is true for every single system. As we said, a certain omega, y1 omega, and then y2 omega. We have simply expanded the matrix 2 by 2, the 2 by 2 matrix, and we got each output, and then we got the input channel to each output. And because it's a coupled system, as you see, the 1 omega affects y1, and the 2 omega affects y1 too. So each output is weighted sum of both inputs. The off-diagonal terms capture input-output interaction. For a scalar system y equals gd, the frequency domain gain is y omega over d omega, and equals gj omega d omega over d omega and gj omega. So I'm trying to just simplify the ratio of y omega, the magnitude, the absolute value or magnitude of y omega over d omega, and we got this gj omega at certain omega again. So, and then the next thing is that if you, let me ask one simple question here just in case. If here either g1 2 or g2 1 go to 0, you essentially have, or both of them simultaneously go to 0, what happens is that this coupling term obviously disappears. Same here. And then we have this ratio, we talked about this ratio, and we can, that's the solution to, sorry, to the example. And then let's think about, or let me just take a look and see if my video has been long enough. If it is, yeah, let's finish it right here. Finish it up right here, and then we're going to continue in the next video. Thank you.